Light, recall, is created by vibrating charges. All electromagnetic waves are created by vibrating charges. Specifically, if the charge is an electron, electrons have very low mass, so they are capable of vibrating back and forth very rapidly. And that's why we get frequencies for high energy waves up to 10 to the 21st hertz. That's 10 with 21 zeros vibrations per second. Let's look at a phenomenon called polarization that has to do with the orientation of the vibration of the electron.
Polarization. In the year 1865, Maxwell proposed electromagnetic wave theory. According to this theory, light is an electromagnetic wave. It consists of vibrations of electric field and magnetic field in a direction perpendicular to the direction of propagation. Also, the vibrations of electric field and magnetic fields are confined to two different planes that are mutually perpendicular to each other. It was proved that electric field vibrations are responsible for the vision. Therefore, vibration of light means electric field vibrations. If we neglect the vibrations of magnetic field, the representation becomes simpler. Now, the electromagnetic wave will look like a pure transverse wave. Every vibrations will have a particular plane of oscillation. The oscillation can be in this direction, and even in this direction. We know that electromagnetic waves are produced by excited atoms. A particular atom may produce electric field vibrations in this direction. Its neighbor may produce vibrations in this direction. Similarly, different atoms of a material can produce vibrations in variety of directions. Due to this, a common source of light like incandescent bulb, candle flame, fluorescent lamp, etc. emit light that have electric field vibrations in a number of directions. This type of light beam, which has vibrations in more than one plane, is called unpolarized light. Similarly, a light beam which has vibrations in only one plane is called polarized light. The electric field vectors in the unpolarized light can be resolved into vertical and horizontal components. Now, this is the simpler way of representing an unpolarized light. However, this is only a front view of the wave. On the side view, the wave is represented in this way. Here, the arrow represents vibrations in the plane of the paper and the dots represent the vibrations in the direction perpendicular to the plane of the paper.
Shown here is my representation of unpolarized light. My representation has not resolved all the vectors into only horizontal and vertical components, like you saw in the previous video. There are various ways to cause light to be polarized, which we'll discuss a little later. First, let's see some examples of polarized light that can be found in the world around us. By the way, our eyes do not detect polarized light. You need a polarizing filter to be able to see the polarization. Let's check it out.
I'm sitting inside my car, and I've placed a few items up on the dashboard. Here's the bright sun glare off my dashboard on the windshield of my car, and now I'm going to take my sunglasses, and you'll see the improvement in vision when the polarized light is blocked by the polarized lenses. There we go. There's the glare. The glare is gone. And if I rotate the glasses this way, you can see the glare is back. Rotating it this way removes the glare, and that's my garage in front of us. You can see inside of it. And now this way, the glare is back.
Polarized sunglasses are polarization filters. A good analogy of a polarization filter is a picket fence. This fence right here would allow vertical oscillations to pass through, but it would block horizontal oscillations. The vertical oscillations you can see can move up and down in the space between the slats of the fence, whereas the horizontal oscillations would bump into the slats and be removed. So that means polarizing filters can do two things. They can either create polarized light or they can block polarized light. So this slide is showing the creation of polarized light. Both orientations, horizontal and vertical, are coming into the fence, but only the vertical is making it pass. So on the other side of the fence would be polarized light. But if the incoming light was only vertical, then it would pass through. But if the incoming light was only horizontal, it would be blocked. Passing light through a polarization filter is one way to create polarized light, but you might have already realized that the glare from the car windshield, it was already polarized when it reached my sunglasses. That's why the sunglasses blocked the glare. It was already polarized. Let's see how polarized light can be formed another way, by reflection. Here I am in my backyard. I'm looking at my reflection in this sliding glass door in the back of my house. And if I take my polarizing filter and place it in front of the lens, as I rotate the filter, you see little to no change in my reflection in the glass. However, if I move off to an angle, now I'm looking at the reflection of the fence in my backyard at an angle. Now if I take my polarizing filter and place it, you can see it does eliminate the reflection. And if I rotate it 90 degrees, the reflection reappears. In this orientation, I see it. In this orientation, the reflection is blocked. That's because at an angle, the light is more polarized, and straight on, perpendicularly, the light is not polarized. And no matter the orientation of the filter, the light can still pass through and we see the reflection. We clearly saw that the light became polarized by reflection off the glass, but only when reflected at an angle. Let's see how this happened. Notice here that we are using the notation for vibration of light waves that we saw at the beginning of the video. The arrows represent vibration in the plane of the screen, and the dots represent vibration in and out of the screen. And the dots and the arrows are perpendicular to one another. Those two planes of vibration represent what we often call the vertical and horizontal components of the oscillations. If you have ever skipped rocks across the water, this can help you understand what is happening. Let's show you. So if you've ever skipped a stone on a pond, you know that nice flat stones work the best. And when you throw them, you spin them like this so that they're spinning like that, so that when they hit the surface of the water, they skip off like that. So you can think of the light the same way. If it's vibrating horizontally, it will skip off the surface of, it will skip off a horizontal surface. But if it's vibrating this way, that would be like throwing the rock and trying to skip it like this, and it would just go kerplunk and go into the water. So a horizontal surface will reflect horizontally polarized light at an angle, but vertically polarized light goes into the water. Or if it was glass, same thing. So the only light that gets reflected off is the horizontal and not the vertical. If it's a piece of glass and it's turned vertically, then it's the opposite is true. Then the vertically vibrating light reflects off, and the horizontally vibrating light is absorbed or passed through.
Now we're looking at my windshield from the back seat, and you can still see the glare of the piece of paper and my eyeglasses case on my dashboard of my car. Now I'm going to take two polarizing filters side by side. There we are. And I'm going to overlap them. And you can still see the glare on the windshield. If I rotate one of the polarizing filters, now you can see through the left side, the glare is still present. Where they overlap, no light is coming through. And on the right side, let me zoom in a little bit, the glare is gone.
So here, of course, in this middle part, one filter is blocking horizontal light and the other filter is blocking vertical light. So between the two of them, none of the light passes through. However, when they had the same orientation, windshield is producing horizontally polarized light. That means this filter is allowing horizontal light through. This filter is allowing horizontal light through. So between the two of them, they both allow horizontal light, and we see it come through. But what's interesting, what you might want to take note of here, is that normally if you take two pieces of plastic and overlap them, where they overlap, it's a little darker because more light is blocked. But really here, you don't see it get much darker at all. That's because the only light that passes through the first filter, all of it can still make it through the second filter. So you see in this region, it's not really much darker than over here or over here.